So thank you all for coming out. This is a great turnout. I'm happy to see you all here. So I'll talk a little bit about the OSIRIS-REx mission, which is a NASA planetary mission that has been, it launched in 2016, so it's been operating for quite some time now. And while I'm going to focus on the sample that we brought back, I know that not everybody may be familiar with the mission, so I'll walk you through a little bit of what we saw at the asteroid and what we're trying to do with this mission, why we're flying this mission. My background is primarily in geology, so I am not so much an astronomer, although as Andrea said, my field kind of bridges those worlds. But my interest is actually rocks and minerals, and so you'll hear a lot more about that tonight. So I wanted to talk a little bit about what I'm going to go through, just so you have a sense of where this presentation is going. So I'll talk to you a little bit about the objectives of this mission. I want to introduce you to a particular type of meteorite. I don't know how much people know about meteorites or the different kinds of meteorites, so I want to make sure I introduce you to that. I want to go through the interesting process of how we actually chose Bennu as the asteroid we wanted to go to out of all of the asteroids that are out there in our solar system, and the science instruments that we put on our spacecraft to look at it. I'll go over some science highlights from the mission at the asteroid, and then talk a bit about how we actually collected a sample, and then what we did when we left the asteroid, and then talk about some of the predictions we made for the return sample, and now that we have the sample, what we have learned from it. So the image over here that probably has been attracting your attention the whole time I'm talking is asteroid Bennu. And this is just a series of still images that are creating a movie of the rotation of the asteroid. And I'll talk about this again more in a minute, but the asteroid's only about 500 meters across. It's a very, very small object, but it has enormous rocks all over its surface. So the mission objectives are sort of highlighted in the name of the mission. So OSIRIS-REx is actually an acronym. It stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. So I'll walk through kind of what those things are. Origins is about us. Where do we come from? Where did the building blocks of life come from? They came from our solar system. Our sun formed, there was a nebular disk, our planets and asteroids all condensed out of that disk, and all the chemistry that was in that system is what made us here today. And we want to go back in time and try to understand what those molecules are, what is the chemistry of the very early solar system. And it turns out that asteroids preserve that information really well. The Earth has very active geology. We have volcanoes, we have mountain building, we have streams, we have all of these things that modify our geology and change it over time. And so that very early record of the solar system, 4.5 billion years ago, is not really present here on this planet. So we can go find that information on asteroids. Spectral interpretation is about a method. That's what I do. I use spectroscopy or light science to basically detect what is on the surface of other planetary bodies. So we interpret the infrared spectra or the visible spectra or what have you. Resource identification is about things like identifying water molecules on other planetary surfaces. Water is actually a resource. It's of interest at the moon as well. If we're sending astronauts back to the moon, they may need sources of water either for long-term station keeping there or even as a source of propellant. Security is about the fact that there are sets of asteroids or asteroids that are called potentially hazardous asteroids. They're also often called near-Earth asteroids because they're not out in the asteroid belt beyond Mars. They actually have orbits that cross the orbit of the Earth. That means that there is some potential that someday, if they're crossing our orbit right at the same time our planet is there, they could impact us. And so we want to know where these potentially hazardous asteroids are and what controls their orbit around the sun so that we can better predict which ones might be truly hazardous to us. And then Regolith Explorer. Regolith just refers to the stuff you saw in the previous picture. We don't call it dirt or soil because on Earth, that implies an organic component like detritus of leaves and, plant matter and other plant matter and all the life that is here in people and animals. On planetary surfaces, we don't have that component. And so we have this term regolith to just explain what is the surface of the object. So, as I mentioned a minute ago, these primitive asteroids really are time capsules. And so they preserve the record of what was happening in our solar system at the very time the sun was forming and our planets were forming as well. And so our science objectives over a 10-year mission were to go and get and bring back a piece of carbonaceous material, and I'll talk in a minute about what that means, what that is, early solar system material from Bennu's surface. And our mission was designed to bring back about 60 grams of material. That's also about 2 ounces or a little over 1/10 of a pound of material. And we'll talk about how much we actually brought back. We also have contact pads, which you'll see when I show you an animation later, that literally just touched the surface rather than actually disturbing the surface, so that we could try to get samples of what was at the very most exposed surface. And the reason we want to do that is because the sun is, everybody saw about the aurora in the last few days, right? Okay, so that solar wind is bringing particles out into the solar system all the time. And those particles hit the surface of things like asteroids and do something we call space weathering. And so we want to understand that process. So we wanted to get some of the very uppermost surface as well as the stuff that we would collect from a few centimeters down. But in order to select that sample and decide where we were going to collect it from, we wanted to characterize the asteroid as a whole. So I mentioned I'm a geologist. When I go out and do field work, I don't just pick up any old rock, especially if it's loose on the ground, if I can avoid it. I will go up to an outcrop and use my rock hammer and chip off a piece because I have context. I know what other rocks were near that one and I can look and make record of what the environment was around that place I collected my sample. If I just pick up a sample, then I take it back to the lab and I don't know where it was, what was around it. I have no context for it, and so I don't know as well how to interpret it. So that's why we want to map the asteroid. Things I'm not going to talk about tonight, I alluded to it a minute ago. There are things that happen that with potentially hazardous asteroids can change their orbit over time. That may cause it to go further away from the Earth, or it may cause it to be more likely to intersect the Earth. And so I'm not going to talk about that science tonight. I'm not going to talk about comparing our observations of the asteroid to observations from the Earth, like telescopes, like this one. But we did do that. And then, actually, let me go back because I want to show you the timeline here. And this is perfect because I'll focus on this. So here's what we did. We had launch of the spacecraft in late 2016. The mission was actually proposed to NASA in 2010. It was selected for flight in 2011. And then we spent that time between 2011 and 2016 building all the hardware, the spacecraft, the scientific instruments, all the software that would run all of that, and making sure that it all worked. And so we swung out into the solar system. We swung a year later. We came back around towards Earth to get a gravity assist that would sort of slingshot us out to where we wanted to meet Bennu, which we did. This is called the approach maneuver in late 2018. So it took us 2 years to get to the asteroid. And then what we did was we went into this asteroid operations phase for not quite 2 years. And we, out here near the end of 2020, in October of 2020, we actually did our sample collection. And then in 2021, we departed the asteroid to come back to Earth. This is really unusual. Most spacecraft go out somewhere. They don't ever come back. And so we actually had to get this spacecraft back to Earth with that sample on board. And what happened was we spent another 2 years coming back. And last September, we had sample return. And that happened, the capsule was released and landed in the Utah Test and Training Range. And then that sample went to Johnson Space Center, and we are now here and are doing our analysis of the sample. So now I have to go back through these. Sorry about that. Okay, so I said we were going to collect a piece of carbonaceous material. So this is based on our understanding of the meteorites that fall to Earth. Meteorites are, the vast majority of times, pieces of asteroids that fall to the Earth, and then we find them and collect them. A very small number of meteorites might come from Mars, and a very small number of them also come from the Moon, but those are much rarer. Anyway, we classify these meteorites based on a bunch of different chemical properties or isotopic properties. And these carbonaceous chondrites are a specific type of meteorite, and they are carbon-bearing, so that's the carbonaceous part. They're also stony meteorites. They don't have very much, if any, free metal in them. So if you've ever seen meteorites like in a museum, there's a cut slab, it's this metal. These are not that kind of meteorite. And so its parent body, and I'll use that term, refers to just the asteroid it came from. Okay, so that's the parent body, the parent asteroid. In this case, those parent asteroids never melted. They never got hot enough to melt on their own. So these are basically what we call sedimentary rocks. If you know geology, there's igneous, sedimentary, and metamorphic rocks. These are sedimentary rocks. So you had little bits of stuff flying around in the solar nebula, and by gravity and just accumulation, these things come together and create asteroids and other small things that eventually become the planets. The other thing they contain are these things called chondrules. And chondrules are only known in meteorites. We don't have them here on Earth in our rocks. And what they are solidified droplets of silicate magma. So a volcano, the liquid part that you see flowing out of a volcano like in Hawaii is called magma. It's liquid rock. And so that's exactly what this is. And I'll show you some examples of what that looks like in a minute. But these are the most primitive, least modified meteorites we have. Even so, some of them show signs of having been altered in the presence of water or the presence of heat. And we know that they come from different asteroids. So in terms of, here's a little bit of the mineralogy part. A silicate mineral is fundamentally made of silicon and oxygen. There are oxide minerals, carbonate minerals, and so they all have different chemical components here. That you don't need to know what those are, just know that they are there. There are different ones, and they form in different kinds of geologic environments. And some of them contain, some of the meteorites contain up to 22% by weight water. It's not liquid water, it's H2O that's locked up in a mineral, but it's still water. And so here are a handful of example minerals that are listed here. So olivine, anybody's birthstone peridot? That's olivine. Serpentine is a mineral that's it's the state rock of California. It's very common in California, and it's what you form when you add water to an olivine. It turns into serpentine. Magnetite is an oxide. There's another very famous oxide, rust, iron oxide. You've all seen rust, you know what that is. Magnetite is also an iron oxide, but it's a different chemical formula, so it doesn't look like rust. And then pyrite, fool's gold. Most people have seen that or had experience with that. That's a sulfur-bearing mineral. So these are all things that we see in these meteorites. Now the question is, why aren't the meteorites good enough? We have all this information, we can look at them. Why do we need to go get something and bring it back? That's a lot of work, it's a lot of expense. In part because of the thing I mentioned a moment ago. If somebody walks up to me and says, here's a rock that came from a volcano, and I say, okay, that's nice. Which volcano? I don't know. Which continent? I don't know. Okay, I can tell you it's an igneous rock, but I can't tell you much more about it than that because I don't know where it came from. I don't know what its context is. So that's why we want to go to an asteroid and do this kind of research. So the next question then is, how did we choose this one asteroid to go to? Now, remember I said we wrote this proposal in 2010. So we had to go based on what we knew in 2009 about the asteroids that had been identified or at least detected at that point. And at that point, there were about 500,000. As of today, there's well over 1 million. But at that time, we were dealing with a little more than 500,000. Now, we knew because of this potentially hazardous security aspect that we wanted to study, we wanted a near-Earth asteroid, not a main belt asteroid out beyond Mars. So that narrowed it down very quickly to about 7,000 asteroids. That's a nice, whittling down, but still, you've got to pick one out of 7,000. That's not easy. So we said, okay, well, what else do we need to worry about? Well, we're not just going there, we have to come back. So we want to go to an asteroid that we know is going to be easy to come back from. And so we had to look at the orbits of these 7,000 asteroids, and we said, okay, there's a little less than 200 that are probably in the best place for us to go. And we said, okay, well, that's still too many. We kind of want to get this down to fingers and toes kind of category. So what else can we use to limit this number? Well, some of the asteroids that we're talking about in this 192 are actually very, very small. Some of them may only be 20 or 50 or 100 meters across in size. And we wanted to operate a spacecraft around this object for a couple of years. And so you need something that's big enough to have just enough gravity. These things hardly have any gravity of their own. They're barely held together. So we said, okay, we need one that's at least 200 meters in size. All right, so that gets us down to 26, and now we're starting to get closer to where we want to be. And then we said, well, we're trying to do this origins thing. We're trying to understand this origins question. So we want a carbonaceous asteroid. Now you're down to 5. And out of that, we looked at just different options, and we said, okay, Bennu is our target. Our backup is an asteroid called Ryugu. And if anybody has followed the Japanese Hayabusa 2 mission, the Japanese sent a very similar mission to Ryugu, to our backup asteroid. And so we've actually now got information from 2 of these objects, which is really quite fun. So here's what Bennu looked like to us at the time. We had a very rough idea of what its shape was, and we actually call this a shape model because it was based on ground-based observations. We didn't have close pictures, we didn't have high-resolution information, but we could estimate how big it was. And so just for reference, this is the Empire State Building and the Eiffel Tower. The day on Bennu is only about 4 Earth hours. It rotates that fast. A year on Bennu is a little bit longer than an Earth year, and its mean density is much, much less than what is typical here on Earth for our rocks. So does anybody know, just off the top of your heads, what has a density of about 1? Yeah, ice and water, yeah. So this is telling us something really important too about what this thing is made out of. The other fun fact is that its average reflectance is only about 4.4%. And on average, the Earth's moon is 12%. The analogy I like to use is that if you were looking at a charcoal briquette, this asteroid would be darker than that. So we had to account for that when we built our cameras because they needed to be able to really almost see in the dark. So we wanted to pick a suite of science instruments that would give us as much of that context as we could collect. So for those of you who are in high school or maybe remember high school, this is your electromagnetic spectrum here. At very high energies, you have gamma rays and X-rays. These high energy waves are harmful to us, which is why you limit your exposure to things like X-rays over the course of your life. But they're useful for interrogating planetary objects. We had a student experiment from MIT and Harvard that was an X-ray spectrometer that was designed to tell us something about the chemicals that make up the asteroid. As we move into the ultraviolet and the visible, this little narrow bit here, this is what our eyes can see. But there's all this other light around us all the time. Our eyes are only just sensitive to this part. And the reason they're sensitive to that part is because that's where the main energy of our sun is. So we see in the wavelengths that our sun is outputting the most energy. And so we had a spectrometer that can see the visible and infrared. So it's the OSIRIS-REx visible and infrared spectrometer. And it sees a little bit into the infrared. We have a camera system that takes pictures, camera system, regular cameras, the OSIRIS-REx camera system. And then OTIS is the instrument that I helped build and worked on, and that's the OSIRIS-REx thermal emission spectrometer. And that's because we're out here in what we call the thermal infrared. This is around 10 micron wavelengths. And so if you've ever seen a thermal cameras tend to show you what is happening. It's heat energy around 10 microns. So you've probably seen an infrared image, whether you knew it or not. And that tells us, these all tell us something about composition. There's a laser altimeter that we use to, it's literally like this thing in my hand that I can push the button, light goes across, you see the red light, and then, but that light, that's traveling at the speed of light. So when I click this button, it takes time, not much to us, but there's time involved in that light going over there, reflecting and coming back to my eye. If I can measure that very precisely, I can tell how far away the wall is. So if I go out to an asteroid and I do that repeatedly and I raster across or go back and forth, I can tell the relative topography of the surface to where I am. So we can make maps of the topography of the surface. So we also finally have a telecommunications system, and we can actually use that to do some studies of the gravity of the object. So here's what Bennu looked like to us first time we really got up close in December of 2018. These are the images that were on that very first slide I had in an animation, and this is what happens if you turn it into what we call a Mercator projection. So this is like if you've seen a map of the world that is just flattened out into a rectangle, and usually in our maps, you know, North America's over here and South America's here and Europe and, you know, Asia and Africa. So this is the same kind of projection of the surface of the asteroid. And so you can see that there are some circular looking features here and there. Those are very old impact craters from other asteroids or other materials impacting the surface of Bennu. So this was, again, what we saw when we got there. It was not what we expected. We had predicted, based on our observations from the Earth, that this asteroid would be largely covered in particles about 2 centimeters in size, about like that. And we designed our sampling system around that. We designed our spacecraft capability around that. And I'll show you in a minute, well, let me just go ahead and do it. This is what that surface looks like up close. This white bar down here is 24 feet, okay? That rock is bigger than 24 feet across. And so most of these rocks are on the order of 3 or 4 feet, and then they go down a little bit, but you really don't see any sandy or pebbly looking surfaces. And so when we saw this, our jaws dropped, and we really had to go back and do a lot of new analysis to figure out how were we going to deal with this. But we did, and that's a real success story for another time. This is one of my favorite images because this is the limb of the asteroid. The rest of it's here in the shadow. And you see these little specks out here. And the first time we saw this picture, we were like, oh, that's really cool. You can see some stars in the background. And then our resident astronomer said, I don't recognize those stars. Those aren't stars. And we started taking more pictures like this. These are pieces of the asteroid that are being ejected from the surface. And we only saw them because we took this angled picture of it, and so these little particles are being illuminated in a way that they normally wouldn't be. And so we realized that either the asteroid was getting impacted by little micrometeorites that were blowing these things off, or maybe our other hypothesis is that what's happening is because this asteroid is turning once every 4 hours, it has no atmosphere. So its daytime surface temperature is hundreds of degrees, and then it goes into the night and it's facing the cold of space. And so it drops its temperature rapidly. For those of you who are adults who drive, you know that maybe you know about frost wedging. You know what it does to a road. In the wintertime, as things freeze and thaw, it expands and contracts, expands. So we think that what's happening is that process, and that as that process is happening, the water is actually exploding these little particles out into space. So among some of the discoveries we made is that Bennu is pretty old. It is about 1 billion years old in its current state, even though we think the rocks that make it up are older. We think Bennu is the product of the impact of 2 much larger asteroids, and it created this little baby asteroid. And so the reason we think it's old, these circular features that are impact craters, if you've ever looked at the moon, you've seen impact craters, and they have these rays shooting out of them. And they have very sharp, defined edges. Well, these are not sharp and defined. They don't have rays coming out of them, and that's what happens with time. It's just like here on Earth. As rocks weather, they degrade physically. The sediment pours off of them and they get rounder with time. And so the same thing happens on planetary surfaces. So we had to look at this surface and start assessing where could we possibly get our spacecraft close enough to this object that we can collect a sample. And so we selected these places as possible small craters, very tiny craters in some cases, where we might be able to do this. And I'll show you these with a scale on them in a little bit. We also saw evidence that rocks had sort of ridden up over other rocks. There's this big giant rock back here, and these rocks somehow got on top of it. So we think that there's something called seismic shaking, that there are tidal forces, there are physical forces that act on the asteroid over time. And if it makes the surface vibrate, then the rocks can kind of skitter along the surface. But there's no atmosphere, there's no water, there's no other means of moving those rocks. Here's a really neat example of a kind of rock that nobody had ever seen on the surface of an asteroid before, and we had not seen anything like this in meteorites. If you look at this little cluster up here and you zoom in, this is what it looks like. And we called these little campfire rings. And it looks like this was a rock that literally just kind of fell apart into these pieces. And you can kind of see an example of what we think it looked like before in a different place. You can see what looks like an intact rock, but it's got these little light and dark areas in it. You can imagine that if you broke this rock between those things, it might fall apart like this. Okay, so water-bearing minerals. Let's talk about water. This is this resource that we care about and we want to know about. It comes in 2 forms, water, which is H2O, and hydroxyl, which is OH. And these compounds are contained in minerals, and a particular kind of mineral called a phyllosilicate. So silicate, again, means silicon and oxygen basis. Phyllo is a Greek portion of the name here, and it means sheet. Anybody use phyllo dough? Same root word, phyllo, meaning layers, and sheets. And so sometimes people call these clay minerals, if you've ever had a reason to use kaopectate. Kao is kaolinite. It is a clay sheet mineral. It absorbs water. So that's how it does what it does. So one of the ways that we can identify these minerals on a planetary surface is with our spectrometers. And so here is a plot of spectral data from one of our spectrometers. And what you're seeing along the x-axis from left to right is the wavelength of light. And then what you're just seeing here, these spectra are offset from each other so that you can see them better. This is just how much light they reflect at that wavelength, all right? And all you need to know is that the shape of that curve changes with what the thing is made out of. That's really all you need to know about this. And so you can see that Bennu has this absorption feature here, and that when we compare it to different kinds of carbonaceous meteorites, we actually see that there's some similarity, most similarity here to this one that's called a CM1. And I'm not going to bother to tell you what that means, but it just helps us narrow down what is the composition of the thing we're looking at. The exact band center here tells us about the chemistry of the minerals around that water. It moves back and forth this way as you change the chemistry of the rest of the rock. And what we know from looking at this position is that our mineral serpentine, this hydrated olivine, is what is indicated by this spectrum. So that's kind of fun. There's another part of the spectrum. I mentioned the FLIR, the thermal camera, the heat sensing camera. This spectrometer does much the same thing. And so I've got wavelength up here for you because this unit is not familiar to most people. But if you think in units of wavelength, you know, our eyes are seeing things less than 1 micron. So this is much longer wavelength light than our eyes see. And then you can see that trace here. This is what Bennu's infrared spectrum looks like. And so when we compare it to meteorites, again, you don't need to know what the difference is between these meteorites. I'll tell you a little bit about it in a minute. But all you need to do is be able to say, which one does it look like? Okay, and that helps you identify it. And so we look at these, and it turns out that I've arranged these meteorite spectra here in order of what kind of geologic environment they've been in the past. And I said that some meteorites have interacted with water. Those are up here. And I said some meteorites have been heated, and that heating can cause chemical changes. And so those are the ones that are down here. And so what we see is that Bennu is most like the things up at the top of the plot that have interacted with water. So that gives us more confidence again that this is an asteroid that's has a lot of water-bearing minerals. We made a specific prediction about the abundance or the fraction of water-bearing minerals in the rock, and we'll talk about how we test that with the sample in a bit. We also saw evidence of liquid water actually circulating through the asteroid at some point in its history. And again, this was something we had never seen in meteorites. There are these things called carbonate minerals. If you know what limestone is made of carbonate minerals, okay? So these carbonate minerals we saw on the surface, these are the pictures, and the scale bar here, this goes from 0 to 2.8 meters. And so I roughly think of a meter as about a yard, a little more. And so we could see these little fracture-looking things, and they're very bright. And where we see this, we see these carbonate minerals in our spectra. And so we had never seen anything on this scale. Some of these have to be centimeters in size, and we've never had a meteorite that was that much carbonate. So we think that these are literally veins where water was moving through the asteroid at some point in time. And then what happens is after the water leaves or it evaporates, it leaves behind the carbonate minerals, okay? And they fill in these fractures in the rocks. And again, we haven't seen anything like that in meteorites. We have also seen, the important thing about carbonate is right here again, the root is carbon. It's a CO-based mineral, carbon-oxygen-based mineral. And so this is easily produced by geologic processes not having anything to do with life. But we also found other carbon-bearing compounds that look a lot more like organic material. And I'm not going to talk too much about that, but we did find it, and it's one of the things we went there to find. So how did we do our sample site selection? So I talked about the fact that the rugged surface that we found was unexpected, and we had to reconsider what we were going to do. When you are flying a spacecraft and you're going to land it on a surface or contact a surface, a planetary surface, you have to model all the things that could affect where that spacecraft is going to go. And you develop what you call a target ellipse. So it's basically a circle or an oval, and you say, okay, we're 99.9% confident that we're going to land somewhere in this circle, okay? Our original target ellipse was 50 meters in diameter. There was nowhere on this asteroid that had a clear space 50 meters in size. The best we could do was to get that down to 10 meters. And so the people who fly the spacecraft, people at Goddard Space Flight Center in Maryland, people at Lockheed Martin down in Littleton, had to figure out how to fly this spacecraft much better than they had ever intended to have to do. And so with this goal in mind, we picked 4 sites. We named them after birds. Bennu is the bird that was a companion in mythology to Osiris, to the Egyptian god Osiris. So I think it was a stork. And so we used bird names to name our target sites. So we have nightingale, kingfisher, osprey, and sandpiper. And we ended up choosing the one here in red. So nightingale is where we went. I'll point out this really big 10-meter plus rock here. It's also probably about 10 meters high. And we had to fly the spacecraft in right past that to get into this location. We were calling this Mount Doom.
So why didn't you choose that location when there was that big dangerous rock?
Because we felt like we still had the best information about that site. It was one of the fresher craters, so it was more recently exposed material. And we just, they all had pluses and minuses, but this one just kind of edged the others out.
So how large of a topography did you know the deployment site would be?
We knew that there would, we had those topographic measurements, those laser measurements down to, centimeter scales. Very, very good resolution. So this is going to loop a bunch of times, and so try not to look at it for just a minute while I explain to you what's going on over here on the spacecraft. So this deck of the spacecraft here is where all of our instruments sit. So our spectrometers are sitting here, our cameras are in different places. This is our antenna for communicating with Earth. And then this thing here is the sample return capsule. So the sample had to get into that thing from the surface of the asteroid. And the way we did that was we had this long arm. And this is about, I think, 15 feet long. And it's articulated, so it folds. And there's sort of a spring in here. And down here is this little round canister thing. And that's what this is here. You're seeing it in side view, where here you're kind of being able to look at it like this. And so the idea here was we weren't going to land the spacecraft. We were just going to barely touch the asteroid long enough to collect the sample and then back away. All right? And so this is showing how we do that. So it contacts the surface, it fires nitrogen gas bottles into the surface to cause the surface to get disrupted. And in so doing, the surface flies in past these little flaps and gets put into the sample ring, which is the container for the sample. And you can see the sample getting added in there. So it touches, gas blows, stirs up the surface. It all goes into this canister in a big ring. And this is what this whole process actually looked like in near real time.
And so that was coming down on that was coming down on a 15 feet.
15-foot long arm.
So that's just a little longer than the height.
Yeah, so the spacecraft was probably up at the roof relative to the ground. That's how close the spacecraft got to the asteroid. And so what you're seeing here is the moment of impact, and then it literally backs away. The spacecraft backs away as soon as it can. We ended up penetrating the surface there about 48, 50 centimeters, which was more than we expected. And we thought, an awful lot of material. But you can see just how much stuff goes flying when we impact and release those gas canisters. So that was a very exciting moment. Now, after we got that sample, we wanted to try to verify somehow that we had material. So one of the things you can do with this articulated arm over here, sorry, let me go back. Oh, no, come back, go back. One of the things you can do with this articulated arm is you can fold it up and then you can tip that canister back towards the deck up here so that you can take a picture of it. And that's what this is. This is a picture of the sampling head. And by the way, I should say post-tag, I didn't define tag, touch and go. If you know anything about airplanes and you know what a touch and go is, it's like you land, you go down the runway and you take off again. Okay, that's a touch and go. And that was kind of what we were doing. So we called this event tag. And so this was the after tag imaging. And what we were seeing here was what concerned us. And let me see if this does what, yeah, okay. So again, these are still images, but they're creating like I think it's just a 3-frame movie. And so if you look right here, for example, there's a particle. And all of these particles, you'll notice, are actually going away from the canister. You'll also maybe see that there's a little bit of a wiggle of dark stuff in here. So there's a flap in there made out of mylar that's holding the sample in the container. There was a rock holding the mylar flap open. And so we thought what we saw here was sample material escaping into space. And the scientist who leads our mission said, oop, there goes somebody's PhD. And so we said, okay, we had planned to do all these measurements, spin the spacecraft around, try to figure out how much mass we had collected, all these fancy things we were gonna do. We saw this happen and we went to NASA. We literally went to NASA and said, we can't do any of that, we gotta close this thing up and go. And they said, we get it, do it. And so that's what happened. So we stowed it, and so the arm brings back the canister, and there it is right there, and it sits down. This thing right here, this is the heat shield. It's been popped up here, so it's like that. And then you pop the canister in here, and these angular things here, there's 3 of them. There's one in back that you can't see. These are little clamps. So you push this thing down, and the clamps latch onto it, and then you disconnect from the arm back here, and then you close this lid, and you bring it back. So we left Bennu in May of 2021. As I mentioned, this capsule landed at the Utah Test and Training Range last September and was taken to Johnson Space Center in Houston immediately to be opened, examined, and for samples to be allocated to our science team, as well as it will be going out to the international community of scientists. And a bunch of it is going to be stored securely for future generations so that 50, 100 years from now, when the technology of scientific instruments has again made leaps and bounds, innovations, there will still be material left for people to study in new ways. And so this is our capsule sitting in the desert. It literally landed perfectly, just like that. So I'll talk a little bit in the remaining time about what we saw when we got into the sample and what we've seen so far. So if you don't remember, at the beginning, I told you we had a requirement to bring back a certain amount of mass, a little over 1/10 of a pound or 60 grams. This is how much we actually brought back. We got back twice what we were required to by our mission design. So that was a tremendous success for us. These little circles look like little Velcro pads. That's exactly what they are. They're stainless steel Velcro. And they do, in fact, have little tiny bits of rock in them that you really can't see very well in this picture. And so those will tell us about that uppermost surface before we went in and penetrated. And then you can start to see some of the rocks piled up over here. And this is the mylar flap exposed over here that's holding all this stuff in. But some of it got out. And so, yeah, so this is just telling you what I just told you.
So were you there when they opened it?
Yes, some of the science team was there. I was on the preliminary examination team. I am on the preliminary examination team. And we were not in the clean room. There's only a couple people allowed in there at one time. This whole thing occurred in a very clean room and within what we call glove boxes. If you've ever seen, for example, an astronaut on the ISS, they've got their arms in gloves in a box and they're trying to do stuff. That box is there to protect whatever that experiment is from the environment. And so with our sample, because we were looking for these very early solar system molecules and organics, we didn't want anything from Earth contaminating this sample to the best of our ability. So all of this was done in glove boxes in clean rooms, like you would see like at an Intel factory where they're building chips and things like that. So we got to watch by video feed, but from another room in the building. So what did we actually see about Bennu that we can look for in the sample? So we saw that there were in fact, and you can see it from that tag event animation, there actually were submicron to centimeter sized particles. Our sample container could only hold particles about 3.5 centimeters in size. So even if we contacted something bigger than that, we couldn't collect it. So we assume that the biggest particle we're going to be able to see in that return sample is about that size. We saw the water-bearing sheet minerals. We saw the limestone-like veins. We saw some iron oxide. We saw some sulfides, and we saw organic compounds. So we saw all of this with our instruments at the asteroid. We saw, if you remember back to that one picture where I said the scale bar was 24 feet and how big those boulders were, you may have noticed that some of the boulders were bright and dark. It looked a little salt and pepper-like. So we had interpreted that there were two different kinds of rocks. We don't know if they differ in what they're made out of or not, or if they're just sort of different colors, different brightnesses. We had determined that there was low density and porosity, a variety of other characteristics that we all took together. And what we did was we said, okay, we've made these observations. We can turn those into scientific hypotheses. And so you learn about hypothesis testing in school, but oftentimes you're like, when does anybody do that in the real world? I do. So we made hypotheses. We said the remote sensing, or what we did from the spacecraft looking at Bennu, has accurately characterized its minerals, its chemicals, and its physical properties, what it looks like. And so we are making an assertion that these predictions are accurate. We will test that prediction with the sample, or that hypothesis. I'll talk about that in a minute. We also said Bennu contains prebiotic or pre-life organic compounds. And we said geological activity occurred inside the parent asteroid of Bennu early in solar system history, and that's because of those veins of carbonate, that water flow. So those are the three things I'm going to talk a little bit about now, but we have all these other hypotheses that we're going to test with this sample, and these hypotheses have several sub-hypotheses in most cases. So characterizing minerals, chemicals, physical properties, we said we thought there'd be two types of rocks based on their brightness and texture. In fact, we see different kinds of rocks. These are examples from this is the return sample, so now these scale bars are only 5 millimeters. So very, very small scale, and you can see these all look kind of angular. This one actually almost looks a little shiny. This is angular. This is Bennu though. So you can actually look at the sample and see things that look a lot like what we actually saw on the scale of the asteroid as big rocks. We also saw this kind, and again, on the left are two things from the sample, and here's a rock on the surface of Bennu. So this is 5 meters and this is 5 millimeters. So the sample, again, looks a lot like some of the rocks we saw. So we see some evidence of those two different kinds of textures. Here's another one that we saw. So over here where Bennu is, you see that little vein kind of thing, that bright vein there that was that limestone carbonate kind of stuff. We see these rocks in the sample. And we didn't really expect these. These were a little surprising, but maybe this is this stuff. And so that's something else we're testing. So here's some of our spectra, and Bennu is up here at the top. It's blue, it's a little harder to see, but this is the same figure I showed you before, except now the next two spectra down are actually the same data from the sample. And here are again meteorites. Now I've constrained these to all be meteorites that had water interactions. And so we really see much more strongly the similarity here. And in fact, our predictions about what the primary minerals were are correct. Here's another one. This is fun. So there's a technique called X-ray diffraction. It basically just tells you what minerals are there. It's just a different way of doing it. And you look at the peaks, and each peak represents something. And certain minerals have multiple peaks, and each set of arrows I'm showing you is telling you about a different mineral that's there. And so this is the phyllosilicates, those clay minerals are the blue arrows. The sulfides, the magnetite, the carbonates, they're telling you how much of each one of those things is there. So that was another way of confirming our prediction about how much of the different minerals was there. And then there's the olivine or the peridote. We also said we thought there were organic compounds, and in fact, when we look at these things under microscopes, you can actually see evidence of these organic compounds. Now, this is not at all my expertise, and so when people who do this for a living tell me that these are organics, I'm like, okay. But these things here, this little scale bar is about 10 microns. The average human hair is about 30 to 50 microns in size, so that gives you a sense. A human hair might fill this field of view side to side. So this is 2.5 microns. And so you can see just how tiny some of these things are. But we confirmed that what we saw is actually in the sample. I showed you this rock that I said if it broke apart, it would look like that little fire ring. That one. This is a slice through one of the samples. And the way we do this is we put it in, if you've ever had a CT scan for anything medical, we can put rocks in a CT scan, just like we can put a person in, and we see inside of it, just the way we do with people for medical purposes. And this way we don't have to damage the sample. We can look inside of it another way. And we see these differences in brightness and darkness, and these look a lot like what we saw in those big rocks on the surface of Bennu. So these are called breccias. All that's a geology word. It just means a rock made up of angular fragments that have been glued together. The boulders, this is a CT scan, and this is a 3D rendering, and in a minute you're going to see us go through the slices of the scan, just like you might see a scan through somebody's brain, for example. And it'll spin around a couple times, just show you what the shape of the rock is. And this bar down here is a millimeter in size. So now we're going into the rock and seeing all these little bits that are getting brighter and darker, and you see them kind of coming and going as we're doing slices through that rock. And then it'll come back. So this is one of the ways that we can visualize what is inside something. So how does our sample compare to what we predicted? Long story short, we did a really good job. We found those water-bearing minerals, those limestone-like things, the oxides, the organics that we went there to find. We did, in fact, find these similar to these carbonaceous chondrites. There are a couple things that we looked at or saw at Bennu that I haven't talked about, and we haven't identified those things yet in the sample, but we think they come from somewhere other than Bennu. So just like we get meteorites, other objects in the solar system get meteorites too. There are meteorites on the surface of Mars. There are meteorites on the surface of Bennu. And we saw some, and we haven't seen any evidence of those yet in the return sample. And then we saw some other minerals that we didn't predict, and so that's been kind of fun. And then those things that were being ejected and blown off the surface, we haven't found anything yet that we can confirm are those kinds of things, because most of them fall back onto the asteroid, but we're still looking for them. So that's all that. And where do we go? That is the end of the story for now. We are still looking at this sample. We literally just made our first public presentation of the science you saw here in March at a scientific conference. So what you're seeing here is very, very new information. And we're continuing to do our analyses. The science team is still continuing to receive sample material from the curation facility at Johnson Space Center. And so I encourage you all, if you're interested by this, you can find us on the web. We're on Facebook, Twitter, whatever Twitter is now, X. You know, all the socials, we're there. Come find us, keep following us, and I'm happy to answer questions.
Start in the back with questions.
You said when you took the sample, the impact was greater than you expected. Was that because the density of the object was less than you calculated?
It wasn't necessarily less than we calculated, but we didn't know what the density stratification would be with depth. And so we didn't know how firm that upper surface might be. And so we went in a little bit more than we expected, but not anything beyond what we designed for.
So when you were playing the video on how it showed the impact on when it got the minerals, when it got off, it showed like a very light part for like 2 seconds. What was that?
That was a flash. What was happening was that the arm of the spacecraft that was going towards the surface, we impacted, but it caused that to bend a little bit, and it was sunlight shining on a white surface. So it wasn't an explosion the way you might be thinking of one. It was just all of a sudden that piece of hardware, that piece of the spacecraft, suddenly had a lot of sunlight on it.
So when you're navigating to it, how long of a lag time is it before your signals go to it and it comes in response? Or do you just target and say go?
So with this spacecraft, we were close enough to the Earth that the light travel time is negligible. It's a few minutes. If you're trying to communicate with Mars, it might be 8 to 12 minutes. If you're talking about, if you know about the Voyager spacecraft, which have also been in the news recently, and they launched in the late 70s, they're way out beyond the sun's influence now. It takes something like 12 hours for a one-way communication at the speed of light to get to those spacecraft. So we still commanded everything in advance. We didn't literally joystick it, but we could respond very quickly when things happen. We could have very rapid communication with the spacecraft. Yeah?
Were there any surprises in your samples that you hadn't expected?
Yeah, absolutely. There was one mineral that we did not detect from the spacecraft, and it's a mineral called phosphate. To compare that to something else you know, this is phosphate. And so we did not anticipate that. It's very uncommon in meteorites. And so it took us by surprise when we did see it. It's a very small fraction of what is there, but it also tends to form in water like the carbonates or the limestone kind of thing. It tends to crystallize when you evaporate water. So we're still trying to figure out how that formed and where it came from, what it means. Yeah.
The spacecraft is on the new mission.
Yes. So the spacecraft, when it flew back to Earth, you have to actually point it right at the Earth. And then the sample canister gets, or the capsule gets released so that it will literally impact the Earth in Utah. But you don't want the spacecraft following it in. So we diverted the spacecraft to go away from the Earth. And because the spacecraft and all of its instruments are still in perfectly good working order, we got NASA to agree to extend the mission lifetime, and we're now called OSIRIS-REx, which is Apophis Explorer. So the asteroid Apophis is going to have a very close encounter with Earth in 2029, April of 2029. And it's going to be a tremendous opportunity to see an asteroid up close. It's not going to impact us, but it's going to come very close. And what we're going to do is catch up to it after it passes by the Earth and go make all the same measurements that we did. We won't be able to collect a sample. Our sample collection equipment is gone, but we can go do everything else that we did. So that's what the spacecraft will do. Yeah.
I'm going to pause for just a second. I think there's some eager kids.
Oh, yeah.
Might...
No, I'm trying to be real quiet about it, so keep going.
Oh, okay.
Yeah, no, go ahead. Anybody who needs to go, go. I won't be offended, but I'm happy to answer questions. Yeah, go ahead.
It's about the collection canister. I heard that it's really hard to open. Can you expand on that?
Yeah. So if you remember looking at that when I said it came back to Earth, you could look down at the canister and you could see those little contact pads around. There were screws in between each of those. There were 24 of them. We got 22 of them out with no problem. The last 2 were just frozen. And one of the things that we have to be careful about, I mentioned contamination of the sample. What I didn't talk about is that even as far back as when we were building the spacecraft, we had to be very, very careful about contaminating things with especially Earth organic material. So, for example, we didn't use nylon on anything, anywhere, because nylon has organic compounds in it. We didn't want that anywhere near the spacecraft, okay? It turns out that when you're dealing with the hardware, you have to use special tools because just regular old stainless steel is kind of dirty from the perspective of what we're trying to study. So the screwdrivers we were using were softer than normal stainless steel. So between the frozen screws and the soft tool, the screwdriver, not the screwdriver was getting stripped. So what they did was they said, okay, we need to figure out a better tool to get in here. So they bagged it all back up, put it away, kept it pristine, went off and devised a new tool that they could use to undo those screws, and then in January they pulled it all back out again, got the 2 screws out right away. So everything is open and all the samples available to us now. Yeah.
Why can't you touch the samples or even anything on the thing with like organic material?
Because we're trying to measure organic materials from the early solar system. We don't want ours contaminating them. So we try to keep our germs, our biology, our everything away from the sample as much as we can. Some of the sample will get exposed to me, my lab, things like that with time, but there are certain other scientists who are making those organic measurements and they need that sample to stay as pristine, as clean as it possibly can. Yeah.
Will I assume lithium-ion batteries, will that continue to power the rest of the mission that's going forward, or do they need to be replaced?
No, the batteries, there's no doing any kind of in-flight maintenance. They'll just keep working. And so I didn't actually mention this, and I probably should have. These 2 little wing-like things, these are solar panels. And so those charge up and recharge our batteries. And so we expect them to keep working long into the next mission. There was one back here maybe that I wanted to get. I'll come back up front. Yeah.
So along the same lines, when it comes to maneuvering the spacecraft, you have to have some kind of propulsion.
Mm-hmm.
Can you discuss that mechanism? What are you using for fuel? And how mindful do you have to be about your fuel level? How close have we gotten? Because you sent it out again, right? So
Yeah.
I'm really curious about
Yeah.
that.
This is all great questions. So there are multiple thrusters on the spacecraft. There's one large main engine that when you fire it really gets you going. But there are all kinds of little thrusters that allow you to make very small changes in where the spacecraft is pointed and what it's doing. I'm going to lean on you. It's a bipropellant system, but I can never remember the 2 components. Do you?
OSIRIS-REx, I'm afraid I don't.
Okay, all right. So, but the propellant is composed of 2 things. think in this spacecraft. I just don't remember. I don't think so. Yeah, I can't remember off the top of my head, sorry. But I bet if you went online, you'd be able to find that, no problem. It's, yeah. So we carry tons and tons of fuel, much more than we would ever need for the Bennu part of the mission. And it turns out that I think, if I remember correctly, when we left Bennu, our projection was that by the time we had gotten back to Earth and were leaving Earth after dropping off the sample, we would still have more than half of our fuel remaining. So we carry a lot of it, you know, because you never quite know what you're going to need. You always want to have way more than you think you need in case something goes hinky, but it didn't. So we have a lot left. Yeah.
Were there any viruses or bacteria discovered in any of the samples?
That's a great question. So none have been identified. Viruses would be exceedingly unlikely because viruses are an Earth thing. If we see a virus in there, it probably came from us. It means we've contaminated the sample. We also similarly don't expect to see any kind of bacteria. That's a relative, in terms of, you know, where life originally came from, it's a primitive life form, but it's still sort of advanced. And so without any kind of source of energy or water, there's no real way for bacteria to live on the surface of an asteroid, and they're exposed to sun.
There was water there.
There was water there at one point, yes, but there was still no atmosphere. And it seems like unless you have enough of a prolonged source of energy and water, and we don't know how long that water was there. In geologic time, it may have not been very long. But yeah, just the general environment in space and the lack of energy source, you know, we're not really worried about that kind of material in the sample. Yeah.
So when the sample was collected and put it in the capsule, did it eject immediately, or did it have to make its way back to Earth and then eject?
That's a great question. So the spacecraft carried the capsule all the way from Bennu, almost all the way to Earth. And then the spacecraft released the capsule the same day it landed on the Earth. So the spacecraft and the capsule were together all the way back until literally just a few hours before it landed.
So then how fast did it go?
When it was coming in through the atmosphere?
Well, like the whole time, like what was the fastest speed?
I'm trying to think. I'm thinking, I'm looking at you again, because I'm thinking it's something, I'm thinking of like the Earth's rotation speed we have to match. I don't do orbital dynamics, if you haven't gotten that. It's, trying to think, is it 3, what's delta V is like 3 to 6 kilometers per second, right? Usually?
Yes. Escaping the Earth is one.
But we're not escaping the Earth, we're just traveling. Okay, so 3 to 6, I was close. So yeah, 6 kilometers per second. So in that amount of time, from here to 6 kilometers away. If you've ever, like a 5K race, a 5K foot race is about, what, 3-something miles? So it's, 3-4 miles in a second.
Well, so are you saying that the orbit was the fastest speed that the vehicle was experiencing?
That was its relative velocity.
Yeah, it is a relative velocity because they're both moving all the time. So you just have to, catch up to it.
Right.
So you have to be going a little bit faster, but you're coming in at an angle, so it's not exactly the same. It's, again, orbital dynamics. I'm a geologist.
The capsule just fell
Fast.
It wasn't guided.
It was not guided, no. It was all about how the trajectory of the spacecraft was flown to point, again, we had an ellipse. The spacecraft has got to go in through this little tiny window until it gets right up close to the Earth. And then once it releases the capsule keeps going on that trajectory. And then the spacecraft diverts. But every few weeks on that return trip, we were making calculations, and I was getting updates every week. Here's the window we've got to hit, and here's where the spacecraft is pointing. And they would use the thrusters if they needed to make little tiny corrections so that the spacecraft would keep heading towards that window.